Welcome to Finite Element Methods. Today, during this tutorial, we're going to solve the Transient Advection Diffusion equation by finite element. In this mass transport problem, a one-dimensional aquifer is modeled using a controlled laboratory experiment. The aquifer has constant area and length of 1 meter. And contaminated fluid is moving through it. A chemical contaminant is measured to have a concentration of 0 at x equals 0. And the contaminant reacts with its surroundings with a rate constant Kr as it moves through the aquifer. It is known that a chemical substance will diffuse in the medium with diffusion D, and the flux of the material is also known at 1 meter. We want to compute the variation in time of the distribution of the chemical contaminant in the aquifer using two quadratic elements. We're assuming that the velocity is constant and the value is given. All right, so the first step is to develop the weak form of the problem. So let's put this. So let's the first step is to develop the weak form of the problem. How do we do to develop this weak form? So we need to form a weighted residual starting from the strong form of the problem, right? From the strong form. Okay. So what is the strong form? The strong form is given by this partial differential equation, U, which is the velocity of the mixture, the derivative of the concentration, which is theta, with respect to x, minus the diffusivity d times beta prime, and all of this is also taking the derivative with respect to x, plus the reaction rate Kr times the concentration, plus the variation of the concentration in time, theta dot. Okay? So starting for this weak form, we want to find the weak form. So we we integrate between xi and xj, and we apply and we want to not normalize, but we want to project. We want to make an orthogonal this strong form, this equation, with respect to the weighted function. So we multiply this we dot it by v, which is the weighted function. Every single term in the of the partial differential equation, right? So, oh, sorry, that's another one. That's another one. I need to put a dot. So this is just kr v theta plus v theta dot. All right? And that's equal to 0. So now if we integrate by parts, we can obtain the weak form. So we want to weaken the continuity of this equation, right? And the main goal is to balance the derivatives. So again, we look for those terms where we need to do that. And those are the only terms that we want to integrate by parts. So in that case, the second term from the left to the right is the only one that we are integrating by parts. The other terms either are balanced or we cannot balance the derivatives, right? With respect to the weighted function v. Now, the result of this integration is the weak form. So the weak form looks like this. So the first term doesn't change because we didn't integrate it by part. The second term changes. So what is inside, what goes inside of the integral is just dv prime theta prime. The third term doesn't change. So we still have krv theta. And the last term doesn't change either, right? And it's not only because we can not balance the derivatives, it's because the integration by parts, or we want to find the weak form of this equation only for those terms that are dependent of well, I mean, theta is, all the thetas are dependent of are vary in time and space, right? But the integration by part is only for those terms whose derivatives are with respect to x. All right, so that's what we want. All right, so this is all what it goes inside the integrand. What is left is to add the boundary terms. So we have v at xj. Let's call this boundary term q. So what is q? Q is d times data prime. Let me finish this and I will make the notation then. And all of this is equal to 0. So what I'm saying is q is just d theta prime. Okay, so that's our natural boundary condition, right? Or our natural boundary term. All right, so next we need to develop the element formulation for a generic element, right? That's the next step. So let's do it here. So now that we have this, let's move to the next slide. So now we have this form. Let's develop the element formulation for a generic element. And we're going to use quadratic elements, a quadratic interpolation to achieve this goal. So it means that with 3 unknown nodal values, so it means that this is a quadratic interpolation, right? All right. So the shape functions for a quadratic element are of this form. So let's put ni. It's x minus xj times x minus xk over xi xj xi minus xk. At node k, at node k, we have that nk is x minus xj, x minus xi, all over x, k, and no, one sec. This is, oh no, that's fine. Yeah, it's fine. Xk minus xj over xk minus xi. And finally, for the last node, we have that x minus xi, x minus xk over xj minus xi, xj minus xk. All right, so those are the 3 shape functions. You can see that all of them are, the 3 of them are x dependent only, right? So our approximate function, theta, for the transient problem, for the time-dependent problem, is also a function of time. So if the shape functions are x-dependent, we want the coefficients or the nodal values to be time-dependent. So theta I t is time-dependent. times ni, which is x dependent, plus theta k which is time dependent, nkx plus theta j t nj x. So we pretty much are we are defining our approximate function by applying the separation of variables, right? So we have the solution, the part of the solution is only dependent of time, and the other part of the solution is only dependent of x, right? We want to put this in matrix form. We have at this vector 1 by 3 containing all the shape functions, and this vector theta 3 by 1 containing all the coefficients, the time-dependent coefficients, all right? So to proceed, we need to determine the derivatives. So let's determine the derivatives. So the derivative we need in space are theta prime, right? So theta prime is, again, prime means derivative with respect to x. So we still have theta it. Now we have the partial derivative of ni with respect to x. And for the other two nodes, the terms are very similar, right? The only thing that changes is the nodal quantity. So now we're doing k, and the next one will be with j. All right, so this is what we have in matrix form. All the derivatives of the shape functions are contained in this 1 by 3 vector b, and the coefficients in theta, which is 3 by 1. All right. The other derivative we need is with respect to time. So we have theta dot. So different from the previous derivative, this time we are taking the derivative of the coefficient with respect to time, and the shape function remains the same. In matrix form, we have a vector 1 by 3 with all the shape functions. And now we have another vector 3 by 1 containing all the derivatives of the coefficients. Okay? So using these derivatives and the relations between the basis functions and the shape functions, we can redefine our weak form to make it the element for the weak form for the element. So which is the element formulation, right? So all we need to do is substitute this V prime by V transpose, and this is 3 by 1, right? So if we substitute any derivative of theta prime by B theta, any derivative of theta dot by N theta dot, and wherever you see V, you replace by N transpose and V prime by V transpose, we can rewrite the weak form that we previously developed, right here, and define the element formulation. So that's exactly what I'm gonna do. So the element formulation is then the integral between xi and xj. Let me make this better. Now, making the substitution, we have for the first term u n transpose b, and all of this is a 3 by 3 matrix, plus the second term, which is d b transpose b, and this is also a 3 by 3 term, plus krnt n, which is also a 3 by 3 term. And with this term, we have all the derivative of the integrand, which is only related with theta, right? So this part of the integral is related with theta. Now we move to the second integral, which is related with theta dot. And finally, we have the force vector, Q. And this Q is just a 3 by 1 vector containing the boundary terms. Zero and kxj t. Boundary terms for the element, right? We haven't got to the part of the global assembly. So this is all for the element. This is the element formulation. All right. So if you don't consider this term here, and you omit the fact that now theta is not only a function of is a function of time, right? What you have on the integral on the left is what we've been solving before, right? But now we need to add this second term. And that's what is new in this problem with respect to previous solutions of the advection diffusion equation, a differential equation. All right, so now that we have the element formulation, we can proceed with we can proceed and evaluate the integrals for the generic element. So if we do that, we will end up. Let's put now evaluate the integrals for the generic element. And we can do that, right? Because if we look at the first integral, all inside, all in that that integral is x dependent. So we can do that, right? There is no problem at all. If we look at the second integral, the integrand is all x dependent too. So we can do that, right? So the result, as a result of these integrations, we ended up in a matrix 3 by 3 multiplied by the vector 3 by 1 theta prime I, theta prime k, and theta prime j, right? I started from the last integral, so now this is the first term, plus another matrix, which is different, but is also 3 by 3. And this is related with theta, which is a 3 by 1 vector. And this is all equal to Q. Let me change this here. It's kind of difficult to follow. Okay. All right. So since we are using two elements, we can, the global assembly will consider these two elements only, right? So my elements with node I at the beginning, node j at the end, and node k in between xi and xj, right, are of the same length, and the position of the node, of the middle node, is in the center. All right, so I'm considering the two elements of equal length. So if we use these two elements, a set of equal length we a 5 by 5 matrix correspond to the global system. So this is the discretization part. Up to this point, I was developing the element formulation. This is what I was doing. Now I need to decide in how many elements I want to divide my domain. I decided to do it with 2 elements. And since my previous definition was that the definition of the element is quadratic, I want to keep this a quadratic formulation or apply this quadratic formulation for the 2 elements. All right? Okay. So now is the time for the assembly. All right. So now we need to define. We need to determine the boundary conditions in terms of the global unknowns, unknown normal quantities to perform the global assembly, right? So let's determine these boundary conditions. So let's determine the boundary conditions in terms of the global unknowns. Okay, so according to the problem statement, we have an essential boundary condition, which is related with theta at x equals 0 for all time, which is equal to 0. So it means that the concentration of the mixture is equal to 0 at the right end of the domain. Sorry, at the left end of the domain. Okay? My natural boundary condition tells me that the flux at x equals L, so the right end of the domain, is equal to, for all time, t is equal to q bar. I mean, there is some value, but I'm just representing this value by q bar. Okay. So now let's get back to the first boundary condition. So for the first boundary condition, if it's 0 at x equals 0 for all time, right? It means that theta 1, yes, t is equal to 0, right? This is how I represent theta for the first node in my global system of equations. If theta 1t is equal to 0, the derivative with respect to time is also 0. Okay? Now, getting back to the natural boundary condition, if Q at XL for all time is equal to Q bar, it means in my global system that Q5 at T is equal to Q bar, right? That's what it tells me, the boundary condition. So at this point, I'm just defining my boundary conditions. That's all what I've been defining so far. So if I go to the assembly, I will have a 5 by 5 global system, right? Which in general, look like this. With theta 1 dot equal to 0, this is 2. And theta 5. So this is my vector with the variation respective to time. My second matrix is also 5 by 5. Right? In general, look like this. The first component of this vector containing all the thetas is equal to 0. Theta 3, theta 4, theta 5. And in my forcing vector, we have that minus Q1 at T 0, 0, 0, right? 3, 0, right? 1, 2, 3, 4. And Q5 T is equal to Q bar, right? That's what we said. Okay. So because my first row, theta 1 dot and theta 1 are known. They are not involved in the solution of the system. So we only consider a 4x4 system of equations. Right? That's all what we do. Okay? All right. So this is after imposing the boundary conditions. Essential and natural, both. So the last four, so if well, that system of equation, that is the one we're gonna use in the next step, is a 4x4 this is 4x1, which is related with theta dot plus 4x4, and the other vector is 4x1 and is related with theta. So the first one theta dot, right? The second one theta. And the forcing vector is a vector which is 4x1. This is, in general, or the general form of this is the capacitance. Theta dot is d dot plus k, the stiffness matrix, times d, data with d equal to f. So this is c, this is k, and this is f. All right. So this is the system, or this is what we want to solve now by finite difference. Okay, this is what we want. So up to this point, all we did is solving by finite element the spatial part of the problem. Now we need to deal with the time, and to deal with the time, we're going to use finite difference. So we have three methods. I'm just going to follow the backward different formula for this. So if we use the backward different, the formula derived for this method looks like this. Where C is the capacitance matrix, K is the stiffness matrix. We need to inverse this term, right, to solve for di, where I is the time step that that we want to know. Because this inversion, this method, is more computational expensive. All right, because that inversion, however, is more stable. So that's why I choose this one. In the second term, we have again the time step delta ti, C the capacitance di minus 1 plus fi. All right. So what do we need now? We need now to apply the initial condition of the problem. I might not say that, I might not say, I mean, probably I didn't say this before, but the initial condition of the problem is that at t equals 0, for all x in the domain, right? For all x in the domain, the concentration is equal to 0. So the initial condition for the problem is that at theta, for all x at t equals 0 is equal to 0. Okay? So if this is true, it means that di minus 1, so d naught, is equal to a vector full of zeros, right? Because this is at t equals 0, right? So now we want to find what happened at t equals 1. At t equals 1, we find d1, and so on. And we can keep applying this formula until we consider that we achieve our solution. All right, so now we go to Mathematica to solve the problem, right? The first part, the first part is all related with the solution of the special problem. So we define for the quadratic element number 1, the basis, the shape functions. We take the derivatives for the shape functions. We build K1 and C1, which are the matrix, the stiffness matrix and the capacitance matrix for the element 1, because the length of the element and the location of the middle node is the same for the second element. We should expect to get K2 and C2 matrices the same as K1 and C1. Once we have the element, the stiffness, the matrices C and K for the two elements, we assemble this in the global system. So we have now one C global, one K global, 4 by 4, right? And one F global, which is 4 by 1. We containing the boundary, the boundary term Q bar. We use, up to this point, we solved the special problem. Now we need to use backward difference to solve, to find the coefficients, which are a function of time, right? So we define that at delta t I, which is my dt here, the time step is 0.01. We define, we're gonna do it this for 20 steps, so n equal 20. My initial condition is that theta, which is represented by t, for all x at t equals 0 is equal to 0. So this is why this vector is 4 by 1 is all zeros. Now in this line is the new line we're using to solve the equation through this iteration. So if we do the do loop, we can solve the equation. All right. So all we have done up to this point is to solve for the coefficients. If we do that, this is what we got. All right. So we have all the values for each node for 20 steps, time steps. That's what we got. Okay. Now the question is, how do I know to verify that my solution is correct? And that probably is the most difficult part of this problem. So the finite element part was the easy one. So I had to do the following. I had to solve the analytical equation, the partial differential equation, which is not easy. So I went to Wolfram documentation. I looked for mass transport. And it helped me that Mathematica has an implementation to solve for this partial differential equation. So I'm not going to go over the details of this, but by following this procedure and maybe making some modifications to the tutorial, I arrived in the solution of the differential equation. As you can see, in the solution, which is represented by the lines, matches or has a good agreement to the finite element solution, which is represented by dots. So we can see that for the second node, remember that for the first node is equal to 0. For the second node, which is represented by blue, is pretty good. We can see a pretty good agreement. And for the last node, which is the one where we apply the natural boundary condition, the similarity is not very good at the beginning, right? But later, up to 0.45 seconds, we can start seeing a better agreement between the two solutions. So if you follow the script of Mathematica, you might find yourself a little bit confused about what you need to do to solve the partial differential equation, okay? But our goal here is not to solve it by this method, is to solve it by finite element. And I think we achieved that goal, all right? But it's good. It's good that you guys know that if sometimes you need some reference, you might to find a partial differential equation, you might find it in the documentation, in Wolfram documentation. All right.